hopefully everybody knows what a set is. A set is just a collection of things. The only thing important in this collection is that there are no duplicates, so there's implicitly some notion of equality between elements, and two elements that are equal cannot be in the same set, so they're all different in some sense. I'm going to represent sets as basically collections of points. Again, these points are not sort of geometric points, they're just like things, right? All right, so what's the big problem about measuring the size of a set, right? Let's see. So suppose you're in a parking lot, right? So you have a fun evening out planned, and you drive into a mall or something, or a restaurant, and you enter a parking lot, right? And we are interested in counting how many cars are there in the parking lot. Well, one way you could count is like on the way in, you kind of keep a counter. Okay, 1 car goes in, 2 car goes in, 3 car goes in, and then maybe somebody goes out, and you have to keep track on things, right? The other thing that a lot of parking lots do is that every parking spot has a sort of light that says whether it's occupied or not, and you count the number of occupied parking spaces, right? So what are you doing? You're kind of counting the number of cars in the parking lot, but what you're doing really is counting the number of lights, right? So there's some device that maybe counts how many lights are on. And how are these two things equal? If you think about it, like, we use this sort of implicit kind of equivalences between two different sets in some sense to count things, right? So one of the fundamental things that we will discuss today is that, well, if you have a set A and then you have another set B, right? And the B could have different kinds of points in it, right? I don't really care about what these individual things are as long as they're different. So, all right. So, and then if you can sort of map between these sets in a way that is, in math, you call them kind of injective functions and surjective functions. So it's kind of the notion of two different elements have to map to two different things, right? So there's a one-to-one map, and it also covers the whole set. Or in other words, equivalently, you can define another one-to-one map from here to there, right? So if you have a pair of these maps, you say that there is a bijection between these sets, and one of the results that is pretty easy to prove is that these sets must have equal cardinality, so equal size, right? So the same number of elements arise in these two sets. So we have these implicit kind of bijections in our heads when we count all the time, right? So that's one of the ways in which we will analyze this problem of counting sets, is that really it doesn't really matter what is in a set as long as they're all different and we're counting the number of different things in a collection in some sense. All right. Let's see some more interesting examples, right? So suppose you park your car and now you want to go into a restaurant, right? Okay, so in a restaurant, this is kind of like a fancy restaurant. Let's say you have a 3-course meal that the restaurant offers, and there are like 4 choices for appetizers, 3 choices for mains, and 2 choices for desserts, right? And one question you might ask is, how many different ways can you design a meal, right? So you are given a choice of between 4 appetizers. You're supposed to pick one of them, 1 main and 1 dessert, and different people might pick different things. So how many such meals is the restaurant offering, right? And again, typically what you would do is just you would multiply 4 and 3 and 2. These are the different choices in some sense, and you'll get some number, right? I don't know, 24. So there are 24 different meals that you can get, right? So in some sense, you're counting the number of elements in this set, where the set is a set of all meals that the restaurant is offering. And in some sense, you're building up that number from the number of choices of different things that are combined, right? So this is a different kind of set. So we'll see what kind of set that is, but just to give you a preview, that's a so-called product set, and it has some connection with this fact that when you are counting the number of elements in that set, you are taking a product of three numbers, right? All right, so that's still a simple example. Let's take another example. So, all right, you have waiters in this restaurant, right? And they're supposed to get paid. And the way they get paid is as follows. They put in some record of how many shifts they're doing per day, right? So let's say, just to keep things simple, there's a lunch shift and a dinner shift. And every waiter basically says, were they there for the AM shift, for the lunch shift? Were they there for the dinner or the PM shift, right? Maybe they just didn't show up one day and they did neither. Maybe they did both. Maybe they did one or the other, right? And at the end of the week, let's say you just want to count how many shifts there are. So how would you go about counting that, right? So I don't know, you could think of maybe just having a 2-element set, right? One that says lunch and one that says dinner, right? And if a waiter shows up for both, then you want both L and D. If it shows up just for the lunch or just for the dinner or for neither, right? So there are 4 possibilities, right? And then this is what happened on Monday, and for Tuesday there is another entry on how many shifts you did or what kind of set of shifts you did, and so on and so forth until Sunday, right? And at the end of the week they want to get paid, so somebody needs to count how many such shifts there are, right? All right, so how would you count such a thing? Well, you can't just take these sets. Let's say Tuesday you did a dinner shift, right? And Wednesday you did nothing. And then Thursday you did a lunch shift, right? If you just take the union of these sets, you might know that when you're taking unions, because the set does not have any duplicates, you will drop some elements, right? So you will say, okay, I mean, the union of these 4 sets is just L and D, so I just did 2 shifts. And that would be bad, right? So you don't want to count like that, but instead you want to, when you're taking the union of different things, you want to sort of distinguish them, right? So another construction in a set that we will learn about is the so-called sum construction. And when you do the sum of 2 sets, you are somehow, you have to guarantee that yeah, you're going to take a union, but the original 2 sets did not have any overlapping elements, right? So that there was no element in common, and so there is no chance of you undercounting, all right? And one way you could do that is by tagging this L and D. Let's say L and D was the choice for Monday. You're going to tag it with Monday, right? And Tuesday you're going to have maybe L and D again. That's fine. You still retain some information that it came from Tuesday, right? And so on and so forth, and maybe Wednesday you did just the lunch shift, and so on and so forth, and let's say Sunday you did a dinner shift, right? And so now if you take the union of these elements, and these elements are now a little bit more structured, right? I mean, there's not going to be any double counting, right? So in some sense, you can now count that you had 2 shifts on Monday, 2 shifts on Tuesday, 1 shift on Wednesday, and so on. All right. So this is just a preview of this other construction called a sum construction, right? So we're going to go into that. How do we keep track of these things? Another thing you could do is maybe count the number of functions. So let's see. How do we count functions, and why would we want to count functions? Well, yeah, let's say you have finished your dinner at this point, And let's say you went to a theater to watch a movie, right? And then you have a theater with a bunch of seats, right? You have the back seats, you have the row in front, and whatever, right? So these are sort of numbered G, F, blah blah, and then 1, 2, 3, blah blah. Every seat has a number or not. I mean, you know that it's the third seat in the back row, whatever, right? So somebody from theater wants to count, just for fun, how many different configurations can people sit in this theater, right? So if it's a pretty crowded theater, then all of the seats will be occupied mostly, but maybe a few will not be occupied. On a different day where there's not a lot of interest, there'll be a very few seats here and there sprinkled, but each configuration is going to be different if, let's say, exactly the same seats are not occupied, right? So how many such configurations would be there, right? So how would you go about counting that? Well, if you think about it, every seat can either have a person in it or not, right? So it's either occupied or not occupied. And let's say you have n seats, right? So you can say that, okay, the first seat, this seat, it could be either occupied or not occupied. The second seat could be either occupied or not occupied, right? So we are following the same logic as we did for counting the number of meals in some sense, right? And you do that for each of the seats, and so that gives you 2 to the power n different configurations, right? So this is good, right? So you can do that, and it might take some time for you to figure this out, but okay, but you know the answer now, right? But another way in which you can think about it is that, well, what if I thought of a function, right? And this function will take a seat, right? And it will tell me, is this occupied or not, right? So is this seat occupied or not, right? So this is either true or false, and the number of seats are, well, n, right? So this is basically a function of a set of seats of size n to a set of outcomes, or I mean, it's a boolean, right? It's true or false, right? So it has two possibilities. So there are two elements in this set, right? And as it turns out, the number of functions of this form is also 2 to the power n, right? And it has to be 2 to the power n because you just count it in a different way. And so the size of this set, of the number of functions that you can create of this kind, you might want to count that, right? All right, so that's enough about introductions. Let's now go into some algebra and make sense of it. By the way, this is a so-called exponential construction because we want an exponential result. So functions correspond to exponentiation. When you want to talk about multiple things in sort of like this and that and the other, like your 3-course meal, right? What is the appetizer? What is the main? What is the dessert? Then that's a product. When you're talking about a choice, is it the AM shift or the PM shift, right? Is it Monday or is it Wednesday? So when you're talking about choices and you want to keep things separate, then that's a sum, right? So that's basically what we're going to do. We're going to just dabble in these 3 constructions and see where it gets us. All right, so where do we begin? Let's do some formal kind of stuff. So we already said that a set is just a collection of elements, and the way we will represent these sets is I'm going to use capital letters to talk about, this is a set, that's the name of a set, and the elements in that set, I will use small letters for them. So maybe you have a 3-element set, and I'm just going to use small a for that and big A for this, right? Another set, if I want to write, well, this might be B1 comma B2, right? 2 elements in that set. All right. So let's see. Before we start into constructions, let's go back to this notion of bijections and see how we can use that to count things, right? So initially we said that we want to consider two sets equal if there is a mapping between them that goes in both directions, right? It maps distinct elements to distinct elements, and it covers the whole thing so that I can also define a reverse map where for everything on the right there is a unique thing on the left, right? If you just had that, then that would be nice. But we can do something even better, right? All we want to do is count these sets. So how about we say that there is another set which, let's say, I call n, where n is literally the set where the elements are all the numbers 1 to n, right? So there are n elements in this set, all right? So I know that I just said that I'm going to use small letters for elements, but for numbers, let's make an exception. So we have n elements in this set, and these are, you can think of these as points, right? I mean, I'm just labeling them as 1 to n. And by our definitions, if A has a bijection with n, then it has n elements, right? And this is kind of intuitive because I can go and intuitively think of the elements in this set. I can say, hey, you are the first guy, you're the second person, you're the third person, you're the nth person, right? So everybody has a distinct number, and there exists some kind of bijection from A to n, right? And back. And likewise, if B indeed had n elements, there would exist a bijection from B to n as well, right? And it's not hard to prove that once you have bijections, you have a so-called equivalence relation. So what's the equivalence relation? Well, an equivalence relation has 3 requirements. And the game here is you have sort of like a universe of things that you want to determine whether they're equivalent or not, right? So the rules are as follows. Everything is equivalent to itself. And you can think of that as, okay, I mean, is a set equivalent to itself in this sense? Of course, like the trivial map that maps everything to itself, all the elements to itself, that works, right? And then the second thing is, if A is equivalent to B, then B has to be equivalent to A. And of course, if you had arrows going back and forth, that's also trivial, right? And the third thing is, if A is equivalent to B and B is equivalent to C, then A is equal to C. So this is so-called transitivity, and this allows you to chain together equivalences. So here you can chain through this n to show that A and B are equivalent, right? So nothing very deep is going on here, but this notion of bijections really has 2 kind of uses here. The first one that I said a few minutes back was that you really do not care about what the actual elements are as long as they're different, and any other relabeling or mapping to another set, as long as it has the same number of distinct elements, it really doesn't matter what those individual elements are, right? And the second use is that there's just a special set which is 1 to n, and you can mediate through that set to count things, right? So this looks like a pretty special set. We're going to use this set quite a bit as well when we're defining sums. But sums, let's do sums slightly later because there is a simpler thing to do, which is products. Okay. So you have A cross B. I want to define what this set is. All right. So what is this set? This set I want to define as pairs A comma B, where A comes from A. So this notation just means that A is an element of capital A and B is an element of capital B, right? So that's my definition of a product. So this is so-called cross product. And what is a cross product? Well, it's literally like you're taking this and this, where A and B exist, and you're creating a new set, which is going to be a much larger set, where every element here has a corresponding person there, but we're literally taking all possibilities. So if there's A here and there's B1 through Bn here, then I will have A B1 in this set, but I'll also have A Bn in this set. And let's say you had another person here, A prime, then A prime will also have its own pairs and so on, right? All through A prime Bn. All of these are elements of set. And the more elements there are, the more this will go. So of course there's a product construction, right? Because you can think of this as, you can diagrammatically represent it in a different way. You can say that there is a sort of like a rectangle where you have all the A's are appearing here, right? So this is A, and all the B's are appearing here, right? And every point here is a pair A comma B, where A comes from here and B comes from here, right? And each such combination is a pair, right? All right, so what is the size of this set? Well, we can use a rectangle to count how many elements there are in this set. And we're going to use this notation called a bar to denote the size of a set, right? So A cross B is the multiplication of the size of A and the size of B, right? The size of A cross B is just a product, right? And that's it. So that's pretty simple, right? To figure out. All right. So we talked about the meal example, how you construct a meal, right? We can talk about other examples as well, right? How many 2-digit numbers are there? Well, the first digit has to be something between 1 and 9, and there are 9 elements here. And the second digit has to be between 0 to 9, right? And there are 10 digits here. So if you multiply these two, you get 90. And of course, there are 90 such numbers, right? So if you listed them out, you go from 1 to 9, and then 10 to 99. There are total 99 elements in this set, and you're going to take out the first few, which are not 2-digit numbers, and you're left with 90, right? So this product thing works. All right. So now let's come to sums, right? And sums are both trivial as well as a little bit tricky to grow. So the only thing that is special about sums is that when you take elements from individual sets and you're constructing the sum set, right? The sum set really cannot afford to have overlaps. And in general, you can't have overlaps. So you cannot basically take that danger that there will be overlaps. So in this set, there needs to be some kind of tagging on who came from A and who came from B. And that tagging is enough to distinguish all the elements, right? Everybody is coming from exactly one of these. There's no element here that did not come from any of them, and there's no element here that came from both of them. It has to be one or the other, right? You can think of these tags as, I don't know, colors or something, right? But you can also think of them as just numbers, right? So if you have, let's say I'm trying to do a brick product of k things, right? So how will I do this construction? I will define this to be, so you'll have an index, right, I, and an element from AI, where AI is coming from capital AI, right? And how many such i's are there? There are k such i's, right? So where is this coming from? This I, small element I. Well, I is coming from the set 1 through k, okay? All right. So you're just going to pick k colors basically, name them 1 through k, and you're going to tag any element that comes from the ith set with that tag, and that's enough to distinguish them, right? And as we saw, like, tagging is important because otherwise the waiter will not get enough money, right? So they will be undercounted. So that's what a sum set is. All right, and then we can talk about exponentials next, or functions, right? All right, so let's see. By the way, I defined a k-array sum. You can imagine a k-array product as well, right? So I defined a binary product, but you can have, instead of pairs, you have k numbers in a tuple, right? K elements in a tuple, and that will give you the k-array product. All right, so let's now take functions, right? So suppose I have a function that, okay, so let me define what this set is. This is a set of functions that takes elements of A to elements of B, all right? So I'm going to define these formally as functions, right? Where, like, what is f? Where f, if you apply f to A, you get something in B, where A has to come from A and B has to come from B, right? And then the usual restrictions in a function apply, where you cannot have the same element mapping to two different things, right? They could map to the same thing. That's what a function is. We never said that this function is special. It's just a function. Don't confuse this with injective functions and so on. So any function that satisfies this will be an element of this set. That's the function set, right? So now how many elements are there in this set, right? Let's say A had 3 elements and B had 2 elements, right? So how many functions are there? Well, you can also think of this as, using tables, except that now every function is a table. So let's take a particular function, right? And I just said that A has 3 elements and B has 2 elements, right? And this is one particular function. Let's call this f1. What will f1 have to do? Well, there will be some number of elements, a1, a2, a3. And now for each element, I have to pick something to return in B. And if I return different things, then those two functions are considered different, right? So two functions are different if they disagree on even one value, right? But of course, all of these functions have to act on each of the elements of A, but they can choose what to return. And so there are 2 choices here, the 2 choices here and the 2 choices here, right? And you can effectively define a function as what A1 maps to, what A2 maps to, and what A3 maps to. And each of them have 2 choices. So the size of this set is the number of functions that you can create using this procedure, right? And clearly, what we have done is for every element of A, you have this many choices. And how many such things do you have to define? Well, the size of A, okay? So that's where the exponentiation comes from, all right? Cool. So let's see. So that basically are all the constructions that I wanted to do, right? And this one might take a while to kind of absorb, but we'll do more examples of this. Now, algebraically, not like practical examples, but this thing that it's really an exponent will really shine through, right? So what are we going to do next? What we're going to do next is show that all of these constructions actually satisfy all the expected laws of numbers that we have, right? So algebraically, you want things like this, like a multiplied by 1. What do you expect that to be? Well, we expect that to be a, right? For any number, when multiplied by 1, we expect it to be the same number, right? So let's say we are using n for numbers, right? So we expect this, right? All right. So there has to be a similar relationship where if I take the product of a set with some other set which I'm going to define, then that has to give back the same set. So let's see if this works or not. What is now the way these things are related is that I want to say that n is the size of a, right? So what is a set that has size 1? Well, it's really any element, but it has to be a 1 element, right? So I don't care what that element is, call it star, all right? So this is a set that just has something called star in it. Maybe star is not so nice to use because we are using kind of x for multiplication. Let's say we use a box for that, right? All right. And then this notion of equality, we are going to replace by this thing that we were defining, where two sets are sort of equivalent, not equivalent, like sort of like, isomorphic if they have bijection between them, right? So we want to show that when A is crossed with a single element set, we kind of get something that is equivalent to A. And that's not very hard to see, right? So if you have a set of points and then you pair them with this one element set, I mean, everybody is going to have that distinct box along with it, right? There are not any more choices for what this box is. This is a one element set and that has to pair up with every element in A. So really you get, how many elements do you get? You get the same number of elements as the original, right? So this works out. So that equality kind of holds, and that's a good thing, right? All right. So what would be a set that has 0 elements? We know that as well, right? That's just an empty set, right? So if these two are similar, then it makes sense that A crossed with the empty set must give the empty set. Because recall the definition of product, right? You have to pair up elements where one element comes from here and the other element comes from there. But nothing comes from there, and therefore nothing can come out in the resulting set. And this bears out because we have that for numbers, right? You multiply something with 0 and you get back 0. So far so good, right? And the reason we wanted to define 1 and 0 so carefully is that 1 in some sense is the unit of products and 0 is the unit of sums. So it's good that they satisfy these nice things, right? But let's look at something else that is more interesting. We have the distributive law, right? We have A multiplied by B plus C. What is that, right? If you think about the size of sets, we would like this to be A multiplied by B, right? Plus A multiplied by C. In terms of sizes, right? This is just a numeric kind of equation that we know holds because of the distributive property of numbers, right? So we might then conjecture that if we took the constructions for sets and we said, well, if I take the sum of B and C and take the product with A, then that should be equivalent to this other set that I construct, where I take the sum of two products, A with B and A with C. Does that hold? Okay, so let's try to prove this. How does this work? All right. So let's unpack the left-hand side. What does it say? Well, it says that I have a large set, but then some of them came from B and some of them came from C, right? And I have tagged these elements with a color that says it's B, right? So I've used 1 as a tag for each of the elements here and 2 for that, technically, if you want to follow the definition. Or just think of them as their tag, right? Okay. And then I take a product with another set A, right? So now think of all the pairs that I'm going to generate from taking the product, right? Well, each element in A is going to product with B, and then each element in A is also going to product with C, right? So now I can say that in the resulting set, there will be lots of elements, but I can always write that as the union of 2 sets where A pairs up with B, right? Where B comes from capital B, and A comes from C, A pairs up with C where C comes from capital C, right? And I wrote union here, but it is true that these sets are actually disjoint, right? So there is no element here that is equal to some element here. Why is that? Well, the first element is either different or is the same, right? So if it's different, then the whole pair is different. If it's the same, then we have to look at the other entry here. But we already said that no B and is equal to any other C, right? So these 2 sets were disjoint. So indeed these 2 sets are disjoint, and if you want to color this in some way and color this in a different way, that's fine. But these 2 sets are disjoint, and therefore the total number of elements in this set will be just the set number of elements in this set and number of elements in this set, right? So this inequality also solves. Alright, so let's move on to exponentials now, and this will be kind of more of the same, but it's kind of pretty exciting to note that everything works out. And if you want to have fun at home, you can probably try many other things out. But we have some more rules, right? We have this to the power 1. What is this? This should be the same thing as A, right? Size of set to the power 1. And what does this correspond to, right? What is this the size of? This is the size of the set 1 to A. So in other words, there's a set of functions that takes a distinct box element to this set A. Now, if you think about it, how would you define a function that goes from a single element set to A? Well, you have to define what this box maps to, which means you're picking out a certain element in A, right? And so the number of functions that you can create here are exactly defined by the choice of which element you pick to map box to, right? So of course the number of such functions will be the number of elements in A, and so that equality holds, right? Alright, so now let's change this to 0. What does that usually mean, right? Just something to the power 0 is supposed to be 1, right? And here, of course, we're making a small assumption that A is not an empty set, because 0 to the power 0 is not really defined. So let's say A is a non-empty set, and so the size of A is more than 0, and you take that to the power 0, you should get 1, right? And this corresponds to thinking about the functions from the empty set to A. And what is a function from empty set to A? Well, how many such functions are there? Well, there is, you might say there are no functions, but of course there is one function, and that function is basically saying, right? It's just has nothing to do, right? There are no elements to map to. That's fine. That's a function, right? The function just needs to map every element in this set to something, right? And there's no work for the function to do, so it's just a function, and so there's just one function right there. All right. finally, let's look at two more things. So what is a to the power b plus c? Well, we know that recall the exponential laws, right? That's just this and that, right? If you multiply two exponentials with the same base, then you basically take the sum of the powers. Is that going to work out? Well, let's see. What does this correspond to? This corresponds to b plus c to a, which means the picture is that you have a b and a c as an input set, and you're mapping to some set a, right? And on this side, you have basically pairs of functions. One of it maps b to a, and then another one maps, c to a, right? So there's a bunch of functions that we have to define here, but they are not functions, they are pairs of functions. And that will tell me how to map elements from B and how to map elements from C, right? So that's great, because imagine what a function from this set to A looks like, right? It has to map every element in B plus C to some element of A. You can decide that I can partition this function into two functions that will tell me how each of the elements of B map to A and how each of the elements of C map to A. So that's a pair of functions, right? And for every function here, you can pretty much basically merge them because the B and C were distinct, remember? So there is no confusion between, like, okay, if you have a function and maps some element of B to A and a C to A, well, they are different functions, so you can partition them cleanly and merge them into this other function, right? So that inequality also holds. All right, finally, we have one more equation and then we end the video, right? But at this point, you shouldn't be surprised that everything works out. Okay, what happens if you do that? All right, when you do that, what do you get? You get this, right? A to the power b whole to the power c. Well, that's just a to the power b multiplied by c, right? What is this? Well, this is a so-called curried function. You give it a c, and out pops another function, which when given a b will give you an a, right? So think of this as like what's like a real life example of this, right? So let's say in Python you said, well, I can define a function lambda x, right? And what will it return? Well, it will return another function lambda y, and then what will that return? That will return, let's say, x plus y. Right? Right? Okay, so it's a nested function. It first takes one element, then it takes second element, waits until it gets both elements, and then it just sums them, or does whatever it wants with them, right? So that's what the functions in this space look like. And what this tells us, in some sense, is that it didn't matter whether you provided these arguments one by one or you just provided them together, right? So here you're saying, give me a pair, one from B and one from C, and I'll give you an A, right? And in fact, you can show that not only are these isomorphic, but you can give them in any order because it's just like pairs, right? You can flip the order, and if you flip the order, then there's still a bijection between these sets. So all of these turn out to be equal, right? So yeah, so that's basically the point. that we want to make today is that there are constructions on sets, and if you care about how big those sets are, you don't I mean, it can get pretty hairy if you want to like open out everything and really think about what is going on and what are the functions and so on. But because you have the power of bijections, and because you know that it all works out in terms of cardinality, like the simple math works out, you can pretty much predict that the size of an arbitrary construction can be expressed in terms of the size of more basic sets. And the way they will be computed is like you recursively keep computing until you get the most basic of sets, and you can just count those sets just simply by intuition. So that's where we're going to end today, right?